Hello, everybody. Thanks for being here today. We're just going to start in a couple moments. Thank you. Thank you for being here. Just letting people roll in. All right. So I'm going to start by just sharing a few of our upcoming webinars in the next few months. On March 26th, we have a webinar with the California Labor Lab that's going to be H5N1 avian influenza, or bird flu, considerations for total worker health approaches and response with Megan Davis. And then our next industrial hygiene webinar will be on Tuesday, May 20th on industrial hygiene strategies to protect emergency responders with William Jetter, and that's in collaboration with the University of Cincinnati Education and Research Center. For more, you can always visit coeh@berkeley.edu/webinars. Here's a link for you. And now for our webinar today. On behalf of education and research centers throughout the country, we are pleased to present the Ergonomics webinar series. This collaborative effort on behalf of each ERC's continuing education program aspires to provide access to current research supported through NIOSH ERC programs. Thank you for joining us today. Today's webinar, Machine Learning and Natural Language Processing Applications in Injury Surveillance and Prevention, is presented by Guarav Nanda and the Northern California Education and Research Center. Just a few housekeeping items first. You will be muted during this presentation. If you would like to ask a question, please enter it into the online Q&A box that's going to be on your toolbar on the bottom of your Zoom screen. We will save some time at the end for the presentation to address as many questions as possible. We'll also have the chat open. Feel free to use it to participate and join the conversation. This presentation is being recorded and will be made available on the Center for Occupational and Environmental Health YouTube page within 5 business days. All participants who logged in with their registration email for the full live presentation today will receive an email tomorrow with a link to an evaluation form that will qualify participants for a certificate of completion worth 1 continuing education contact hour. Once the evaluation is completed, you'll be able to access and print your certificate. Now, we are pleased to welcome our presenter, Guarav Nanda. Dr. Guarav Nanda is an assistant professor in the School of Engineering Technology at Purdue University, with a focus in industrial engineering technology. He works on research problems involving applied machine learning, text mining, and intelligent decision support with applications in safety, smart manufacturing, and STEM education. Guarav, I'll pass it over to you. Thanks for being with us today. Let's make sure that you can share your screen. All right, you should be good to go.
All right. Are you able to see my screen?
Yes, looks great.
Okay, yeah. Hello, everyone, and welcome to today's webinar. And I would like to thank COEH for giving me this opportunity to present some of the results that we have been working on related to injury surveillance and prevention and using machine learning and natural language processing approaches. So a quick overview about my research. So I work on research problems involving applied machine learning and natural language processing and trying to develop intelligent decision support systems by using the complementary strengths of humans and AI models. So humans, they are good at creative problem solving and they have a lot of experience and domain knowledge. And on the other hand, the AI models or the machine learning models, they can quickly analyze a large set of data and efficiently do analysis, large scale analysis. So how can we combine this to develop intelligent decision support systems that can assist humans? And the intention is not to replace them, as like a lot of people fear that is AI going to replace us. Our goal here is to make jobs easier for the people. And there are some key questions related to it because these AI models, they are very dependent on good quality training data, and which is hard to collect. So one of the key questions is how can we collect good quality training data in a least invasive manner and in a secure manner so that we are able to collect data of real world physical processes without interrupting the flow. And then how can we efficiently combine the insights from multiple sources of data which can be validated and through expert knowledge. And we are able to also validate the data points that we are collecting. And on the delivery side for the intelligent decision support system, how can we design the systems that can be used by a large and diverse group of people effectively? So that is another challenge. And I work on these, especially related to safety, injury prevention, injury surveillance, and also smart manufacturing. So in today's webinar, we will talk about injury surveillance and some of the work that we have been doing related to it. So unintentional injuries, they are pretty common and they cause a lot of like deaths and severe injuries across the world. Here we have some of the stats that like how unintentional injuries impact people. And if we go into the history of safety and injury prevention, so earlier they were being thought as a chance event that happened once in a while. But later on, think 1920s, 1930s is when systematic study of injuries and accidents started. And then there are various models that have been developed for injury analysis, and people started looking at what are the circumstances and what are the factors that are causing these injuries. And with advancement of data collection and data analysis techniques, injury surveillance really, like took off in the past few decades, where we have the data being collected at hospitals when anyone visits the hospital or emergency rooms, or if there are injuries happening at workplace, there is injury reports being created, which are submitted to OSHA. And then also the insurance claims, they will have information about how the injury happened. So this data that we collect helps us in analyzing what were the causes of injury and what were the circumstances that led to certain kinds of injury. And then we can perform statistical analysis and then try to identify what are the leading causes and circumstances and how the prevention strategies can be designed to avoid or minimize the risks that can lead to these injuries. So first step is injury coding. So the data that is collected either through the hospitals or through injury reports or insurance claim, that is unstructured in nature. And that is like the raw data is in form of textual narratives that describe how the injury happened. So for example, in the emergency room, the nurse would type it out, or in a workplace report, the supervisor will write it out. And that data, conducting statistical analysis on that is not easy because that is unstructured data. Now, that unstructured data is transformed to a more structured form through injury codes and through injury coding, which is assigning these cause of injury diagnostic codes, such as what was the nature of injury, what was the cause of injury, what was the intent behind the injury, which body part was injured, what was the major injury factor or the product that was involved in the injury. And so these kind of codes, once the raw data is transformed into these codes, then we can do analysis or statistical analysis on how the injury happened, what are the patterns, what kind of circumstances are leading to what kind of injuries. So then we can identify the leading causes, and we can do the root cause analysis, identify the safety regulation and product features, for example, that need to be updated so as to prevent those injuries. Now, this injury coding was like traditionally done manually. So there are injury coders who would read these raw injury data narratives, and then they would assign these codes. So they would be given the rules, how these codes should be assigned. They would be provided some training, and then they would go about assigning these codes. So there are different coding schemes that are used. So in the US, there is the OX coding scheme, which is more focused on occupational injuries. Then there is the WHO coding scheme, or the ECO, external cause of injury coding scheme, which is also used for more, that covers more general types of injuries. And there are variations of the WHO coding scheme that are used in different countries. So we collaborate frequently with the Queensland Injury Surveillance Unit in Australia, and they have developed their own coding scheme based off of the WHO coding scheme. Uh, Now, some of the key issues related to manual coding are that there is some level of subjectivity involved, where different people are reading the accident description and assigning these codes, and which leads to them thinking that which is the most applicable injury code. So, for example, if there was multiple injury codes, like there was a bicycle involved and there was a fall involved, there is a separate code for bicycle accident and there is a separate code for fall accident. But some people may assign it as a bicycle code, and some people might assign as a fall code. So depending on how they interpret the narrative and their experience level, there is inconsistency in the way people assign these codes. Also, these are in like manual injury coding is time consuming. So for a person to read the injury narrative and then select the most applicable code from the list of codes, that is time consuming. So then in past like 2 decades or so, we have started using machine learning models for doing the injury coding. So these machine learning models, they can be trained on historically coded data, and then they can learn the patterns, and then they can predict the code. And some of the key challenges that are involved with machine learning models, we'll talk about that. So some of the traditional machine learning models that have been used for these are the naive Bayes, the support vector machine, the logistic regression. These models are traditional models. More recently, deep learning models, and now there are also large language models that can be used, which have much more like capabilities. But we'll talk about some of these traditional models, how these have been used, and then what are some of the challenges that have been experienced with that. So one of the key challenges that happens with using machine learning models is there are a lot of codes. So for machine learning models, if they have to classify data, if there are limited number of categories from which they have to pick the most applicable category based on the input data, it is easier for the model if there are limited number of categories, but with large number of categories, these models struggle. So for example, the external cause in the data set that we worked with the Queensland Injury Surveillance Unit, there were about 30 external cause codes, and the object or the major injury factor, there are about 185 codes were there. So for any machine learning model, this is very challenging to assign the most applicable code based on an like input narrative, which is a couple of words. And other challenge is that the data is heavily unbalanced. So the data that these are the 30 injury like external cause of injury codes, and this is from a 500,000 injury data set, and you can see how the data is distributed among different categories. So which is a reflection of how injuries happen in real life. So for example, falls and then struck by or by an object and struck by person. These are some of the most common causes of injury. They account for almost 60% of the total unintentional injuries. But there are several categories where which are there, but there are not enough cases for those categories. So when the machine learning model tries to learn from the training data, it will see like disproportionately higher number of examples of fall or struck or other more popular types of injury causes. But the causes of injury which do not happen very frequently or are rare, they do not like the machine learning model is not able to learn from them. There are other issues that, so we talked about the large number of injury code categories and heavily skewed distribution of categories. There are other issues that these injury narratives, they are typically very short, 4 to 5 words, and they are noisy. So they are not written in like a proper English language. They are use some abbreviations. There are words that mean different thing in different contexts. For example, the word back, it could mean that it was back of a person, or it could mean a location that the person was standing in the back of the car and when the car was moving backwards. So those things make it challenging for the machine learning models to understand the or predict accurately the cause of injury based on the input word. So these are some of the challenges, and even there are misspellings, so it wouldn't be able to resolve on its own. We as humans, we can locate a misspelling and we are able to resolve it, but for the machine learning model, it is difficult. There are also inconsistencies in the manual coding of data, which is used for training. So if the machine learning model is seeing the same narrative, but it is seeing examples in the training data set that for the same narrative, different codes are assigned. So it will not be able to allocate proper weights to each of the uh, categories, and it will not be able to make correct predictions. Okay. Also, the traditional machine learning models, they were just using statistical distribution of words, and they were not able to utilize the semantic or syntactic information of the words in the narrative. By semantic, we mean the meaning of the words, what is the contextual meaning of the word, and syntactic information is how the subject, object, verb, or what are the linguistic relationships between the different words in the narrative. But we as humans, we can see that and we can utilize that information if people are doing coding manually, but the machine learning models are not able to do that on their own. Now, the more recent ones, like the deep learning models with word embeddings and the large language models, they have some capability of doing that. But again, the data is this is still very noisy. So we have done some experiments with the deep learning models and the large language models. So they are better than traditional learning machine learning models, but yeah, there are some limitations in that. Now, then we started looking at how to deal with the low prediction accuracy of machine learning models for rare causes of injuries and cases which are complicated that might have like multiple causes of injury or the cause of injury is not clearly mentioned. So how can we improve the prediction performance of those model. So when this study was conducted, most of the previous study in this area, the maximum they had used was about 40,000 training cases. And in this study, we systematically studied if we increase the training data size from 25,000 to about 450,000 and look at the prediction performance of like the models for predicting the external cause of injury codes, then what is the impact of increasing the training data set and can it solve the problem of the disparity between the more frequent causes of injury which were being predicted with high accuracy or as compared to the rare causes of injury which were being predicted with the low accuracy. So these are some of the results, and you can refer to this paper for more details. But what we found was that as the size of training data set increased, the prediction performance of the like less popular or less frequent categories also increased. But the gap between like this shows the weighted average, which is just based on like the overall accuracy. And the unweighted average is basically it's independent of the size of the category. It is just if there are 30 categories, we take the accuracy of each 30 and then take an unweighted average of that. So we saw that there was an increase in the unweighted average accuracy of almost all the models, support vector, logistic regression, and multinomial naive Bayes. But there was like an asymptotic gap that remained between the weighted average and unweighted average, even after we provided like 450,000 training data set cases. So this meant that there were enough examples for the machine learning models to learn uh, about the smaller categories, but the bias that was there in the data, the imbalance distribution, it was not able to deal with that because internally these models try to optimize the overall accuracy, and for that reason they overpredict the the more popular categories. Next, we looked at the approach of how can we improve the performance of the machine learning model using some of the natural language processing approaches. So we tried to provide the syntactic and semantic information of the text into the model. So we did syntactic tagging, and this was like tagging what are the subject object verb relationships in the text, like what is the subject, what is the verb, what is the object. And then we also used hypernym mapping. So hypernym means the higher level form of a word. So for example, the car, like the sedan or SUV, both are automobiles. So automobile is the hypernym of, for example, sedan and SUV. So we tried that, and we found that if we did that in a non-targeted way, if we just assign tags to each of the words based on the syntax and then transform them into hypernyms, that did not improve the prediction performance if we do it in a non-targeted way. Then if we also tried doing it in a targeted manner, so we looked at the theoretical models of different types of injury. And there are, as I mentioned earlier, there are different models for accidents. And for example, this is a sequence model for how a fall happens. So if it happens due to a slip, for example, then wet or slippery surface should be there. If it happens due to tripping, there should be an obstacle, and then later on there should be evidence that the person fell. So if we look at the narrative and if we try to identify, uh, look for these evidences in a targeted manner, we found that those kind of linguistic rules helped in improving the prediction accuracy. Another example was the energy transfer model, which is again an accident model where there should be evidence of energy, evidence of host, and there should be an environment or the instrument which should be there, and there should be evidence of contact. So we looked for these evidences in the text by using the subject-object-verb relationship and then by using the hypernyms, and we used the word2vec, which was a word embedding model, which was like launched in 2017 around that time. So we use those to look for these evidences, and if these evidences were found, then it was highly likely that for example, in this case, it would be an electrocution or it would be a fall type of accident. So overall, we found that none of the machine learning models were accurate enough to be able to do the entire coding by themselves. So we used the strategy for filtering. So if we are able to use the machine learning models in a way that they accurately code a large portion of the data, and then if they are able to filter out the cases which the machine learning model is not able to code correctly, then those cases could be looked by expert coders. And here we started this work with two very simple models using naive Bayes model, the single word naive Bayes model and the two word sequence naive Bayes model. So the two word sequences, they are like better predictors for certain categories. Like here, the example is for fall. So fell off is generally representative, or fell down is representative of falling off from a height, which is a different category as falling on the same surface. So we used these models, and then we used the agreement between these two models. And along with that, we used prediction strength threshold. So the naive Bayes model, it outputs the prediction along with the posterior probability that this prediction is going to be correct. So for example, the prediction may look like that depending on the narrative, it is going to be a fall, and the posterior probability is 80%. So that means the model is 80% sure that it is going to be, it is a fall type of accident. Now that posterior probability could be less also, it could be 35%, which is indicative that the model is not very sure what is the type of accident, and there might be other types of injuries that are likely to happen. So these are some of the classification results. Now, what the approach that we used was, if the two model, the single word and the two word model agreed, then we take the prediction of that model. And if they did not agree, we would filter those for expert review. So in this case, we look at the overall sensitivity, which is the accuracy of the model. So the single word model by itself was 66% accurate, and two word sequence was 69% accurate. But after filtering 26%, on the remaining data, it was accurate. Like the accuracy was 80%, where both the predictions from both the models agree. Now, if we assume that these 26% of cases will be coded perfectly, accurately by the human coders, the overall accuracy estimate was 85%. And if we used the agreement between single word and two-word model, and we applied a prediction strength threshold of 0.95, which means that if the posterior probability was less than 95%, we don't take that prediction. We filter it. So we filter 45% of the data, and we achieved an accuracy of 86% on the remaining data, where they agreed on the remaining 55%. Now, again, if we assume everything is coded correctly on those 45%, the overall sensitivity was estimated to be 92%. So here we can see that even if we like filter half the data and we have people look at half the data, there is a big jump in accuracy. We also estimated what is the level of accuracy in manually coded data, and we can refer to the paper, and it came to be around 80% or so. So if we use a hybrid semi-automated system like this, where we are utilizing the machine learning model along with the few experts, the overall prediction accuracy or overall coding accuracy was found to be better. Now we also can provide decision support for the part where they are doing the manual coding. So if we provide the top 5 prediction or top 3 prediction of the injury codes to the human coders, that will uh, be very helpful, because this here we looked at the accuracy of top 5 predictions. It was almost like 95% accurate. So even if the top prediction of the machine learning model was not accurate, the top second, top third, the correct category was within top 5, 95% of the time. Now, this would be very helpful for human coders that are new, that are less experienced, and instead of them having to select from like 45 different codes, they can they would have to select from top 5 codes. So we implemented this system at the Queensland Injury Surveillance Unit, and there is another paper that we did in 2023 where we looked at the impact of this decision support system. So it helped in improving the coding time as well as accuracy. So the coding time was improved by around 11 seconds, and the accuracy was improved by, I think, around, yeah, I don't remember the overall improvement in accuracy, but yeah, it helped in like coding the data faster as well as more accurately. Then we looked at different filtering approaches. So we talked about agreement and prediction results of different machine learning models. We looked at like logistic regression, different naive-based models, and prediction strength-based filtering. So filtering on the posterior probability, or the logistic regression model also provides likelihood of prediction. So we can put a prediction strength on filter on that. Then we also looked at agreement and prediction results between models which were trained on balanced and unbalanced training sets. So the unbalanced training set, by that we mean the natural distribution of data, which is like most of the injuries happen in like 2 or 3 causes, but there are 30 different causes. And for the balanced training set, we took about close to 1,000 training cases for each category. There were some categories where we did not have 1,000 training cases, so we just used whatever we had. And then the machine learning models that were trained on the balanced data, they tended to overpredict the smaller categories, and the machine learning models that were trained on unbalanced data, they tended to overpredict the more frequent categories. So we looked at the disagreement between the two predictions and we filtered them out. Another filtering approach that we use was hierarchical clustering. So first we try to identify the broad injury group, like transport accidents or animal related or contact related or falls. And then there was other group which like essentially combined a lot of rare categories. Now, once we predict what is the top level group of injury, then there was separate machine learning models that predicted in sequentially what might be the individual causes of injury within that. So that was another approach for filtering. And then we use the causal rule-based filtering. So these were linguistic rules that were designed based on the accident causation models. So similar to what we saw, like the fall sequential model for fall or the energy transfer model for electrocution. So these rules were like expert developed, and these linguistic rules were applied again to filter the whether if there is missing evidence of any of the component, then that case would be filtered irrespective of what the machine learning model has predicted. Now, in filtering, one of the key things is how much data that needs to be looked manually and what is the overall prediction like accuracy that we are going to achieve. Ideally, we should only be able to filter those cases which the machine learning model is not able to predict correctly. Now, if there is no previously labeled data available, it's a challenging problem that how can the model know beforehand whether it is going to be correct or not. So these are the filtering approaches, and we try to evaluate the efficacy of these filtering approaches based off of what proportion of cases were filtered for expert reviews and what is the overall weighted average sensitivity that we were able to achieve. And you can refer to this paper for more details. But what we found out was if we were using prediction strength threshold and if we used the linguistic rules along with the prediction strength threshold on the logistic regression model, that gave us the best results. So with less filtering, it was over here. So with less filtering, only 25% filtering, we were able to achieve the almost very good accuracy. I think it was about 0.92 or something. And these are other approaches where we had to almost filter like 50% of data, but it is the same level of accuracy. Okay. After that, another challenging problem was that we worked on was assigning multiple causes of injury together. So till now, we were trying to predict one type of injury code based on the injury narrative. So based on the narrative, we tried to predict what was the cause of injury code, or on the same narrative, we tried to predict what was the object that was involved. Then what was the nature of injury? So those predictions were made separately, but if the all the codes together should make sense. So for example, if it was a bicycle accident, the type of injury is less likely to be a burn injury. It would be either like a fall injury or a struck injury. And similarly, the intention has to follow along. Like there should be a logical grouping of these codes. So in this paper, we tried to predict the three causes of injury, like three types of injury codes: the intent, the major injury factor, and the external cause of injury code together. So together as a unit. And then we try to again use different filtering approaches that would filter the cases if any of these three predicted codes were like if they are not predicted correctly, it would filter those cases, because for correct analysis or correct prevention mechanisms, we need to first have the injury analysis done correctly. So here also we looked at different like filtering approaches, and we evaluated which filtering approach worked better. Okay. So after that, looking at all the different filtering approaches, like more recently, large language models also started were available, and then we started to look at the capabilities of large language models and how do those compare with human coding as well as traditional machine learning models. So in this study, we conducted a user experiment where we have the users look at injury narratives, and then they would assign one of these 6 injury codes: cut, fall, struck, burn, motor vehicle, and other, and based on the narrative. And we would then we used eye tracking basically to look at what are the words in the narrative that they focused on when they were making the decision about which is the most applicable code. So that gave us insight into what they were thinking and which words were important for them. And for machine learning models, we use the explainable AI approaches to identify if the model is making the decision for like the prediction based off of the narrative, which words in the narrative were most important for the model's decision. And same for LLMs, the large language models, we identified which words did the LLM use focused more or assigned highest weights for making the classification decision. So for LLMs, we use again prompts, but then we did a validation by removing those words from the narrative and then checking if the LLM, how it is impacting the LLM predictions. So this is the, for example, the screen, what it looked like. So for here, you look dropped weight of 20 kg onto right hand, and it explains the narrative. And then they had to select the most applicable injury code, and they would do a think aloud where they verbally explained why they selected this. And we also recorded the eye tracking data. So we did a validation of the eye tracking data with the verbal recordings for the think aloud data. And then we compared the prediction, and we also compared the explainability aspect, like which words were the models looking at. So what we found was that the machine learning model that was trained on almost like 100,000 cases, and then the traditional machine learning model, it was able to predict better as compared to a non-trained large language model. And like user participants who were not experts, they were like mostly university students and staff who participated in that, but they knew English. And we also did an analysis of, depending on the complexity of the narrative, how that impacted the outcome. So you can read some of the results in this paper, and there we are still working on some more publications from this study. But one of the interesting findings that we had was, even though like different models like humans, large language models, and machine learning, they looked at the same words, but then their conclusions were different. So that was interesting to note. And yeah, the last study that I would want to talk about, we are still working on it, is basically injury surveillance using data on the internet. So this traditional cycle of data reporting and processing, it takes like months to get processed, and especially for product injuries, during that time, injuries still keep happening. So we wanted to see how we can use data that is available on the internet for basically doing injury surveillance. So there have been studies that looked at, for example, Amazon reviews and other sources to identify where if how people explain secure like safety concerns about the product. Previous studies have found that Amazon, there are very few data points that are there for basically which mention about product injuries. We looked at Twitter and we looked at the Reddit data as well. So we found on Reddit where people were explaining, and we took the use case of skateboards. So then here we tried to extract data from Reddit through their API. And then we trained a RNN, a recurrent neural network model. We created data sets from the national injury surveillance data from the CPSC as injury cases and non-injury cases from Amazon reviews, where we filtered out the like product injury related anything. And then we tried to predict the in whether the Reddit post was injury case or non-injury case related. And these are some of the initial results. We are still working on getting the results from here. And yeah, so this is something which we are working on. So yeah, these are the like these are where the some of the applications of machine learning and natural language processing for like injury surveillance. So yeah, I will stop here. I think about time. So I'll be happy to take any questions. Thank you, everyone.
Thank you, Dr. Nanda. That's been a really interesting presentation, and we have a couple questions. The first question that came up a few times was the injury surveillance data. Are you considering like different industries when you look at where injuries happened in the workplace? So are you focusing, or can you focus on, for example, hospitals or in construction?
Yes, yeah. So it depends on the like data source. And for example, one of the studies we were working with the OSHA data. So in OSHA injury reports, they mention where the data is coming from. So for example, we looked at foundry injuries specifically. So we were able to identify like in foundries what kind of injuries are happening. We also looked at like some approaches for identifying whether the injury was work related or not when the injury was reported in the hospital emergency room, because there they don't explicitly mention that. But from the narrative, we were trying to look for identifiers that whether this injury was work related or not. There are like certain fields apart from narrative, like the activity that the person was doing or the location where they are, which can indirectly indicate about the injury being work related or not. But there are complications, like a lot of people do work from home or they are not in a proper occupational setting. So the lines blur sometime in those, yeah.
Got it. Thank you for that answer. Um, I have another question. It seems like it's about the source of data and like the various text fields that you're using from the electronic health records.
Mhm.
Um, this person says, using the text data, EHRs have multiple tables and locations for text data. What were
Mhm.
the data fields used for training, and were they used for all of the records, as also some, as you mentioned, have more extensive and limited texts? Different
E-
text sources used in the different EHRs might be helpful to learn more.
mhm.
Also, with level of accuracy and sensitivity, how did this apply, especially for lower frequency injuries, but incredibly important injury mechanisms, and even more so regarding intent? Let me know
Yeah.
if that makes sense. I can also have the person follow up.
Yeah, sure. Yeah, no, that's a great question. And yeah, so they correctly mentioned like there are depending on what hospital information system they are using, there are multiple fields in which data can be entered. And lot of times, what we have seen is people do not fill all the data because the triage nurses, they are under pressure.
Mm,
And for example, in some of the agencies that we have been working with, uh, different hospitals had different like they were getting data from different hospitals. So different hospitals had different ways of entering information. But as a agency, like a governmental agency who is combining the data from multiple information. So one approach they used was they took all the data and then combined it into a single narrative field. In some cases, the narrative field had how the information of how the injury happened, and there were other fields like what was the activity that the person was doing, what was the location that they were in, what was I think the way they were brought into hospital. Was it through an ambulance or did they come by itself? So those were other fields that were partially filled. But injury narrative or the plain text narrative where they had to enter the information, what happened, that was almost filled every time. Now, there were times where that field did not have any useful information about how the injury happened. It would just say like slipped and fell. But
mm,
that is not telling us what happened, whether was it in a bathroom, for example, or at any other location. So then we try to use these other fields, and we did some of the studies where we used data from different fields. So there was a paper that we did where we used a Bayesian network model where input from different fields were taken, and we developed a Bayes net, and then we tried to predict the cause of injury. So it worked well, definitely, because it was adding independent information into the predictive model apart from the narrative text. So the prediction accuracy improved. But yeah, the challenge remains that all of the fields, they are not filled every time. So yeah, so they can be used if the data is available. If it
mm.
is not, then yeah. And,
Yeah, then you can't use it.
yeah.
That makes sense.
Mhm.
We have another question. I believe this question is about like health record keeping and
Mhm.
billing,
Mhm.
and the kinds of codes that you're mapping to machine learning. This
Mhm.
person is asking, do the machine learning algorithms also map to ICD-10 or CPT codes?
Mhm.
I believe those are for diagnoses and also treatment and like billing insurers.
Yes, yes. Yeah, they do. So the like the machine learning models, and that's good that I mentioned the ICD code, because the transition from ICD-9 to ICD-10 happened like couple of years ago. So we had a lot of training data that was coded in ICD-9. So, and then the prediction we had to make in ICD-10. So there were few studies that came out that mapped the ICD-9 with ICD-10 codes, and then we used like a common denominator for both the codes, so that if we replace the ICD-9 codes with these common codes, and then we use the same code for predicting the ICD-10 code. We also are working on one of the studies with the Australia and NIOSH here, where we are trying to look at how the coding systems of two different countries align, and like if we can cross code each other's data, because that would increase the size of the training set and the diversity of accidents, especially for the smaller or rare causes of injury. And how will that work out? Like there would be some inherent differences in the data from like two different countries or two different setups, like occupational injury data versus non-occupational injury data. There will be some differences, but if we are able to combine those, can the predictive model be improved or not? So yeah, so it depends on how we have trained the data, because if we want the predictive model to predict a certain like coding scheme, for example, ICD or OX or whatever,
Mm,
we would have to create a mapping of the output with the input data that is already there in the training
mm,
set. And then we replace the input data with the mapped output code, and then we retrain the model, or we just, after the model makes the prediction on the training data codes, we transform those training data codes to the prediction data codes. Yeah. But
got
yeah,
it.
cross coding is something that we are working on. It's a
Mm,
challenging problem because there is not like a one-to-one mapping between different coding schemes.
got it. Thank you for that answer. I have a similar question. I believe this is what the attendee is asking, but
Mhm.
asking if there's a bias in selecting a proper injury code based on the mishap reports, and generally, like, how would you deal with the issue of bias based on these different codes and kind of the inputs that you get?
Yeah, there would be bias. So if there was bias in like the training data set, that bias is learned by the model, and that bias would be there. And that is why like those filtering approaches, they trend to like deal with the bias. We talk about different approaches where we try to identify cases which are not predicted correctly. Now, we are also looking at some of the explainable AI approaches where the bias could be we can identify why this model is biased. And if we know why, like what are the phrases or what are the words that are causing those biases, they can be dealt at it.
Mm,
But yeah, the biases would remain as long as there is bias in the training data. And there is bias in the training data. We have seen that. So we would have to find a way to deal with the bias. The either like within the machine learning model or after the machine learning model has made those predictions, we use some sort of linguistic rules or some
mm.
sort of filtering mechanism to deal with the bias.
Got it. Got it.
Mhm.
We have time probably for one more question. I have a question about using this approach in sort of broader ways. Someone asked, have similar classification models been tried with near miss narratives to
Mhm.
better identify hazards in particular? So not just when an accident happens, but the kind of potential for an accident to happen.
Mhm.
Um, and then I was also wondering about the issue of like repetitive strain and perhaps not an injury that happens just in one
Mhm.
moment, but over time as somebody is working and repetitively doing one task. Is there a
Mhm.
way that you could use machine learning to identify that as well?
Yes. Yeah, sure, definitely. Because the near misses, I think they are reported in a lot of different occupational settings. So we were like working with some of the manufacturing companies, and they had a mechanism in place to report the near miss incidents. So the idea again is to, because in a near miss, almost everything is there, but the accident just did not happen, but all the
Mm,
circumstances were there. So
right.
that is useful data. So now the near miss data is like if it is recorded in the narrative form, definitely. And there are, I think, I recall there are papers that have used machine learning model on the near miss data. I think one of the papers I can recall was for firefighters. So those were probably firefighters. I'm not 100% sure, but there was near miss, like predicting near miss incidents using machine learning. It would follow the same mechanism. Like we would train the model on the narrative, and then the prediction would be the type of near miss accident that was happened. So yeah, most definitely yes. And we can also use the injury data for predicting the outcome of near miss data because they are similar in nature.
Got it. Well, thank you so much. We're about at time. I just wanted to let everybody know as well that you can email Dr. Nanda for the slides from today. His email is still up on the shared screen right here.
Mhm.
Thank you everybody for coming, and we hope to see you soon. And thank you, Dr. Nanda, for presenting with us today.
Sure. Yeah. Thank you very much for the opportunity, and thank you all for attending.
Great. Everybody have a wonderful day. Thank you.
Thank you. Bye.